As it feeds, intestinal absorption releases nutrients into the blood and increases blood glucose, increases insulin, activates glycogen synthesis, and tissue absorption by glucose, producing ATP. When glycogen is at maximum size, cleavage and production of fatty acids that are directed to adipocytes occurs. When a period of fasting occurs, the blood glucose concentration becomes low, and glucagon production increases. Glycogen cleavage occurs to maintain blood glucose, and tissue glucose consumption is reduced, and ketone bodies are produced. If blood glucose reduces further, it reduces tissue consumption, and the production of ketone bodies continues. Following the graph, we initially have exogenous glucose, glucose from food or intravenous at 1. Glycogenesis occurs, the absorption of exogenous glucose and conversion to glycogen, reducing excess blood glucose by 2. Gluconeogenesis occurs to balance the concentration of blood glucose at 3. In case of prolonged fasting, gluconeogenesis continues to cleave glycogen to convert to glucose at 3. Looking at the divisions in the graph above divided from 1 to 5, we have phase 1 absorption of glucose by tissues, and the brain primarily consumes glucose, because glucose is abundant in the circulation. In phase 2 and 3 there is glucose absorption into the liver, muscle and fat to reserve, and reduces consumption in other tissues, as they must be with high concentration of ATP. The brain continues to consume glucose primarily. In phase 4 the glucose concentration begins to fall, and the glycogen becomes glucose. The tissues begin to consume less glucose, and the brain uses the ketone bodies in addition to glucose. In phase 5 glucose concentration tends to be lower, so all tissues and the brain tends to further reduce glucose consumption. The brain continues to use glucose and ketone bodies. If it occurs that the person eats at any of the phases, he returns to phase 1 again. The resting muscle mainly uses fatty acid, which enters the mitochondrial matrix, and is the target of beta-oxidation, producing NAD and FAD2 and acetyl coenzyme A, which feeds the citric acid cycle, and producing NAD and FAD2, which go to the chain of electron transport for ATP synthesis and oxidative phosphorylation. In moderate activity, glucose is also used, increasing oxidative phosphorylation, and increasing respiration. At rest the average is 50% oxygen consumption, and in activity it can reach 90%. When exercise is extreme, there is not enough oxygen, blood flow increases to provide more oxygen, but without oxygen to generate all energy, muscle consumes all ATP. Phosphocreatine is used to form ATP, but phosphocreatine is low, thus the muscle will use its glycogen reserve, and the pyruvate is transformed into lactate, generating NAD+, thus fermenting. Glycogen is broken down into glucose 1-phosphate, converted to glucose 6-phosphate and enters glycolysis, forming pyruvate, and transformed into lactate in anaerobic condition, forming acetyl coenzyme A, feeding the citric acid cycle. When pyruvate comes from glucose it spends 2 ATPs and produces 4 ATPs, resulting in a profit of 2 ATPs. But when it comes directly from muscle glycogen there is the expense of 1 ATP, and the production of 4 ATPs resulting in 3 ATPs. Thus glycogen in muscle is important in extreme exercises. Moderate and constant exercise would therefore be a great tool to maintain weight as it uses fatty acids. The heart muscle is sensitive to pH reduction, so it would not be good to use fermentation, so most of the heart muscle energy comes from fatty acid. But at a high glucose concentration the heart can use pyruvate from both glucose and lactate from skeletal muscles and
If you are looking for more content from different areas, visit the reformadorstesad.com website. News and detailed content can be found. With system of research and organization of